Hello, and welcome to the fifth and final video on complex numbers. In this video, I'm going to be discussing phasors. So, most applications of complex numbers are related to oscillations or vibrations or waves or any sort of phenomena where there's a repetitive action. So there's something vibrating or moving back and forth. And the reason for this is really because of Euler's formula, because these complex exponentials contain cosine and sine. And those are functions that model oscillations. And so in order to begin seeing how this works, let's consider sinusoidal functions, general sinusoidal functions. And by sinusoidal functions, I mean functions of the form that are shown at the top of the slide there. Y equals a times cosine of omega t plus phi. So this function contains three constants, a, omega, and phi. The variable is t, which think of as being time in this case, but maybe it could be something else. And so those three constants have special names. A is called the amplitude of the oscillation. It's how tall the waves are. Here would be A. Omega is the angular frequency of the oscillation. It corresponds with how rapidly the wave is moving up and down in radians per second. And then phi is called the phase. It's in radians, and it controls how the sinusoidal function is translated either left or right. So note, I call them sinusoidal, but you may notice that they're defined in terms of cosine functions. However, the sine function is the cosine function translated by pi over 2. And so it's really the same to define them in terms of cosine or sine. And we use cosine by convention. All right, so here are some examples of sinusoidal functions. The top one is y equals 3 times cosine of t plus pi over 6. You note that the amplitude is 3, so the tops of the oscillations are at 3, and the bottom is at -3. The angular frequency is just 1 radian per second, and the phase is pi over 6. This corresponds with the fact that the cosine wave is moved over by pi over 6. And here we have another example of a sinusoidal function. Y equals 3/2 or 1.5 times cosine of 2t minus pi over 2. Here, the amplitude is 1.5, means the height of the wave is 1.5. The angular frequency is 2. Note that the oscillation is faster here. And the phase is -pi over 2. And this corresponds with the fact that this peak is shifted over by pi over 4. Note it's pi over 4 rather than pi over 2 because of the angular frequency is 2. Okay, so these are some examples of sinusoidal functions. Now let's discuss what are phasors. How do we describe these sinusoidal functions using complex numbers? Well, we define a complex number, really a complex valued function, x, which is the amplitude of this sinusoidal function, times e to the I omega t plus phi. So omega and phi are the angular frequency and the phase. Using Euler's formula, this complex valued function would be a times cosine of omega t plus phi plus I times sine of omega t plus phi. And the sinusoidal function y is the real part of x. All right, and now this complex valued function can be written as a complex number, labeled here as z, is a to the e, a times e to the I phi times e to the I omega t. And z is what we call the phasor. And note this z is a complex number. It's here expressed in the exponential form. So it's naturally given to us in the exponential form if we know the amplitude and phase of the sinusoidal function. The amplitude of the sinusoidal function is the modulus of the phasor, and the phase of the sinusoidal function is the argument of the phasor. So a and phi. So note that this z, known as the phasor for a sinusoidal function, so each phasor, once we're given a frequency, omega, corresponds with a sinusoidal function. The amplitude of the phasor is exactly the modulus of z. The phase of the phasor, the phase of the sinusoidal function is the argument of z. a key point, one of the reasons why it's useful to introduce phasors to describe sinusoidal functions, is that the phasor of the sum of two sinusoidal functions with the same frequency, omega, is the sum of the phasors. So you just would have a phasor for each sinusoidal function and add those together. And we'll see why this is by looking at some examples. So let's first look at this example which is shown here. Just find the phasor for this given sinusoidal function. So the sinusoidal function is y1 equals 2 cosine of omega t minus pi over 4. All right, so remember the modulus of the phasor is the amplitude of the sinusoidal function, and the amplitude here is simply 2. And that equals the modulus of the phasor. I'll label it Z1, corresponding with Y1. And the argument of the phasor is equal to the phase of the sinusoidal function. So the phase is equal to negative pi over 4 here, and that is the argument of the phasor. All right, so straight away we recognize what the exponential form for the phasor is. So the phasor is 2 the amplitude or modulus of the phasor times e to the negative I pi over 4. And let me just point out that if we wanted, we could use Euler's formula in order to find the real and imaginary parts of the phasor. So this would be 2, and then use Euler's formula here. Be cosine of negative pi over 4, which is 1 over square root of 2, minus sine of pi over 4, that's sine of negative pi over 4, times I, which would be I over square root of 2. And so this would be square root of 2 minus square root of 2 times I. That's the phasor, either written in the exponential form or in terms of the real and imaginary parts. And so notice that y1 can be written as the real part of the phasor times e to the I omega t. It's the point of introducing the phasors. A lot of times when we're working with sinusoidal functions and applications, we just forget that we're really taking the real part and just work directly with the complex numbers. You'll probably see this if you take further classes on waves or oscillations in applications. You just work with the complex numbers and consider the phasors. You have to remember that really for the real application, for the real oscillation, it's the real part of the complex number. Okay, we will look at another example of finding a phasor. Find the phasor for this sinusoidal function y2, which is given. And this one is initially written in terms of the sine function rather than the cosine function. So we have to put it into the normal form with cosine rather than sine. And we can do that by using the fact that cosine and sine differ by pi over 2, or translations of each other by pi over 2, is shown on the bottom of this slide. So this is equal to 3 cosine of omega t minus pi over 3. That's the sine from before, minus pi over 2. We add an additional phase of minus pi over 2. And so this is 3 cosine of omega t minus 5 pi over 6. And so now we can easily see what the amplitude and phase are for this sinusoidal function. The amplitude is 3. And so this is going to be the modulus of the phasor, labeled as Z2, corresponding with Y2. And then the phase of this sinusoidal function is negative 5 pi over 6. and this is equal to the argument of the phasor Z2. And so we can easily now write down the exponential form for the phasor. The phasor is the modulus 3 times e to the negative I 5 pi over 6. Now if we want to find the real and imaginary part, we can write this as 3 modulus times cosine of negative 5 pi over 6, which is negative square root of 3 over 2, plus I sine of negative 5 pi over 6, which is negative 1/2, so negative I over 2. And so we can now see the real and imaginary parts are 3 square root of 3 over 2 minus 3/2 I. Right? So this is the phasor for this second sinusoidal function, shown here, y2, 3 sine of omega t minus pi over 3. All right, so we found the phasors of these two functions, and to finish off this set of examples, look at the phasor for what we get when we add these two sinusoidal functions together, y1 and y2. These are the ones from the previous two examples. And the key thing here is that they have the same angular frequency, omega. And so that means that when we add these two sinusoidal functions together, the phasor will be the sum of the phasors for the individual sinusoidal functions. All right, so let's remember the phasor for y1 was 2 e to the negative I pi over 4 in exponential form, or square root of 2 minus 2 square root of 2 I in the real and imaginary part form. The phasor for y2, by the way, we called this one Z1, is 3 e to the negative I 5 pi over 6 in exponential form, or negative 3 square root of 3 over 2 minus 3/2 I in the real and imaginary part form, and this was Z2. All right, and so now we have that a new sinusoidal function is given by the sum of these two, the superposition we call it. Y is y1 of t plus y2 of t. And y1 is the real part of the phasor times e to the I omega t. So the phasor for y1 is z1, e to the I omega t. And y2 is similarly the real part of the phasor for y2, z2 times e to the I omega t. All right, and so the real part, the sum of real parts of complex numbers is the real part of the sum. And so this is the real part of z1 e to the I omega t plus z2 e to the I omega t. And then we can factor e to the I omega t out of those two terms. This is the real part of z1 plus z2 times e to the I omega t. Right? And so what we see then is that z1 plus z2 is the phasor for the sum of these two. Right? This is z, the phasor for y, the sum of y1 and y2. And so the phasor for y z is equal to the sum of z1 and z2. So z1 was 2 e to the negative I pi over 4. Z2 was 3 e to the negative I 5 pi over 6. Right? Or if we wanted to write it in the form with the real and imaginary parts, and use these formulas for the Z1 and Z2, and get that this is square root of 2 minus 3 square root of 3 over 2 plus I times negative square root of 2 minus 3 halves. And to identify the real and imaginary parts for the phasor of the sum of the two. Okay, so this is the end of this video and the end of the section on complex numbers. We looked at this application of complex numbers, and this goes quite deep. So there's a lot more to studying waves and oscillations using complex numbers, but this gives us an idea of why complex numbers apply. So we can use the phasors to define these sinusoidal functions. All right, in the next section, we're going to study differential equations.